You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Open source dependencies form the backbone of modern software, powering everything from web frameworks to cryptographic libraries. Yet, while they offer speed and efficiency, they also introduce risks that must be carefully managed. The purpose of dependency management is to ensure that these external components contribute to software stability, security, and legal compliance throughout the lifecycle of an application. Left unchecked, dependencies can harbor vulnerabilities, outdated code, or problematic licenses that undermine the entire project. By treating open-source code as part of the supply chain, rather than as free, consequence-free building blocks, organizations can build applications that are both resilient and trustworthy. The goal is not to avoid open-source components. Doing so would be impractical, but to control their use through careful selection, continuous monitoring, and disciplined update strategies. In this way, teams turn potential risks into managed, predictable assets. Open-source dependencies are essentially third-party packages, modules, or libraries incorporated into applications, container images, or development tools. They allow developers to reuse existing solutions instead of reinventing the wheel. For example, instead of building a cryptography algorithm from scratch, a team can integrate a well-tested library. However, these dependencies come with hidden baggage. They often bring in other transitive dependencies, meaning one imported package may pull in dozens of others. Each of those becomes part of the application's attack surface and operational complexity. While the convenience is undeniable, the responsibility to track and manage them falls squarely on the development and security teams. In effect, dependencies extend the trust boundary far beyond an organization's own codebase. The risks associated with dependencies fall into several distinct categories. Vulnerabilities are the most obvious bugs that attackers can exploit to gain access or cause disruptions. Malicious packages represent another concern, where attackers intentionally publish harmful code disguised as useful modules. Licensing obligations also carry weight, since different licenses impose restrictions on how software can be distributed or monetized. Finally, maintainer sustainability is a subtle but growing risk. If a critical library is maintained by just one developer in their spare time, the likelihood of neglect or burnout becomes a real threat. Understanding all four categories helps teams see dependencies not just as code, but as living obligations with technical, legal, and human dimensions. To manage these risks, many organizations employ software composition analysis, or SCA, tools. SCA scans an application to inventory all the open-source components it contains, along with their versions and licenses. It then cross-references this inventory against databases of known vulnerabilities and license restrictions. For instance, it might flag that a particular version of an encryption library contains a high-severity flaw, or that another component uses a copyleft license requiring derivative works to be open-sourced. By providing visibility, SCA tools allow teams to make informed decisions about which dependencies to keep, update, or replace. Without such visibility, managing risk is like navigating a maze in the dark. Version pinning and lock files offer another crucial layer of control. Version pinning means specifying exactly which version of a dependency to use, rather than allowing updates to float to the latest release. Lock files capture the full set of versions, including transitive dependencies, to ensure that every build is consistent. This prevents the so-called works on my machine problem, where two developers see different results because of slight version mismatches. Deterministic builds, where the same input always yields the same output, depend on pinning and lock files to ensure reproducibility. This not only stabilizes development, but also simplifies debugging and security reviews, since teams know exactly which versions are in play. Semantic versioning, often abbreviated as SEMVer, is the convention that communicates compatibility expectations in version numbers. A major version change, like moving from 2.x to 3.x, signals potential breaking changes. A minor version, such as 2.4 to 2.5, adds new features but remains backward compatible. A patch version, like 2.4.1 to 2.4.2, fixes bugs without altering features. Understanding this system helps developers decide how risky an update might be. For example, a patch-level upgrade may be low risk and urgent if it addresses a security flaw, while a major upgrade may require extensive testing. Semveer offers a common language for developers and maintainers to coordinate expectations about stability and change. To maintain tighter control over dependencies, organizations often use private registries or proxy servers. These act as centralized repositories that mirror public package sources while filtering or restricting what is approved for use. By funneling all dependency retrieval through a controlled registry, teams can enforce policies, ensure availability, and guard against tampering. For example, a company might decide that only packages reviewed and approved by its security team are allowed into the registry. This model reduces exposure to sudden upstream changes or malicious uploads. It is similar to a corporate library where only vetted books are stocked, ensuring employees access reliable content rather than questionable material from unknown publishers. Attackers have learned to exploit developer habits by creating typo-squatting packages. These are malicious libraries published under names that closely resemble legitimate ones, hoping that a developer will mistype a command and inadvertently install the wrong package. Defenses against this risk include restricting allowed namespaces, whitelisting only known sources, and enforcing strict dependency declarations. In some cases, automated tools can validate package names against approved lists. The practice may seem like a minor safeguard, but it blocks one of the simplest and most effective social engineering tactics in the open-source ecosystem. Much like registering fake website domains that resemble real ones, typo-squatting depends on tiny errors that strict controls can eliminate. Another related hazard is dependency confusion, where attackers exploit the precedence of public packages over private ones. If a private package shares its name with a package published publicly, a build system might mistakenly pull the public version instead. This opens the door for attackers to inject malicious code into otherwise trusted systems. To defend against this, developers must enforce scoped resolution, explicitly telling systems to prefer private sources, and ensure package names are unique within the organization. This practice is akin to ensuring your company's mail is delivered to the correct address, not intercepted by someone else with a similar name on a different street. Dependency confusion has led to major real-world breaches, proving it is more than just a theoretical risk. Checksum and signature verification serve as integrity checks for dependencies. A checksum is a mathematical fingerprint of a file, and if it matches the expected value, the file is likely unaltered. Digital signatures go further by proving not just integrity but also authenticity, confirming the publisher's identity. When developers verify signatures before using packages or container images, they ensure that the code came from a trusted source and has not been tampered with in transit. This is comparable to verifying that a sealed letter has both an intact envelope and the sender's verified stamp. Skipping these checks leaves organizations vulnerable to supply chain attacks, where attackers replace legitimate packages with malicious ones during distribution. A software bill of materials, or SBOM, provides a complete list of the components, versions, and licenses contained in a shipped artifact. Think of it as the ingredient label on packaged food. Just as consumers want to know what they are eating, regulators and customers want to know what software contains. SBOMs enable transparency, simplify vulnerability management, and support compliance requirements. When a new vulnerability is disclosed, teams can immediately check their SBOM to determine whether they are affected, rather than scrambling to search through code manually. The practice of publishing SBOMs is becoming increasingly expected in both government and commercial contexts, elevating it from a nice-to-have to a critical part of modern software delivery. Licensing adds another dimension of responsibility. Open-source licenses fall into categories such as permissive, which allow broad reuse with minimal restrictions, and copyleft, which impose requirements like releasing derivative works under the same license. Permissive licenses, such as MIT or Apache, are generally easier to adopt in commercial contexts. Copyleft licenses, such as GPL, carry obligations that may conflict with proprietary distribution. Developers must understand these differences to avoid legal and financial consequences. For example, inadvertently shipping code with a copyleft dependency could obligate a company to open source its entire application. By maintaining visibility into license types, organizations protect themselves from both compliance failures and unintentional intellectual property risks. Security disclosures often come in the form of common vulnerabilities and exposures, or CVEs. Each CVE provides a unique identifier for a specific vulnerability, along with details about its impact and potential fixes. By referencing CVEs, developers and security teams can coordinate responses and track issues across tools and advisories. CVEs provide a standardized language that allows everyone from vendors to customers to discuss vulnerabilities clearly. For example, a team might say, "We are vulnerable to CVE 2023123445, and everyone knows exactly what issue is being discussed. Without this system, communication about vulnerabilities would be far more fragmented and confusing." To prioritize responses, teams often rely on the Common Vulnerability Scoring System, or CVSS. CVSS assigns a numerical severity score to vulnerabilities, factoring in elements like exploitability, impact, and scope. A vulnerability with a CVSS score of 9 or higher typically demands immediate attention, while one with a score of 3 might be addressed in a later cycle. The scoring provides context for decision-making, helping teams allocate limited resources to the most critical problems first. It also supports reporting and compliance, since organizations can show that they prioritized responses in line with industry standards. Without such a framework, patch management would become a guessing game rather than a structured process. Update cadence policies help translate vulnerability data into practical actions. These policies define how quickly patches should be applied based on severity, asset criticality, and exposure. For instance, a critical vulnerability in a publicly exposed web service might require patching within 24 hours, while a low-severity bug in an internal tool could wait for the next scheduled update cycle. Having predefined timelines prevents hesitation or inconsistency, ensuring that responses are both timely and predictable. Update cadence transforms patching from a reactive scramble into a disciplined routine. By aligning with the risk appetite of the organization, these policies ensure that security is maintained without overwhelming teams with constant emergency work. The final piece of dependency risk management is tracking end-of-life status for components. Dependencies that are no longer maintained represent hidden liabilities. Without active maintainers, vulnerabilities go unpatched, documentation grows stale, and compatibility issues accumulate. Detecting unmaintained dependencies allows organizations to plan migrations or forks before problems become critical. In some cases, a team may need to assume ownership of a library through forking to ensure its future viability. End-of-life tracking is much like monitoring the expiration dates on critical supplies. Ignoring them invites risk, while proactive management ensures continuity and stability over time. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Pull request automation has become one of the most efficient ways to keep dependencies up to date without overwhelming development teams. Automated systems regularly check for new versions of libraries and create pull requests proposing those updates. These proposals are then subject to the same tests, reviews, and approvals as any other code change, ensuring that updates are vetted before merging. By automating the detection and proposal steps, organizations reduce the lag between the release of a fix and its adoption. For example, if a security patch is released for a popular web framework, automation can raise a pull request within hours, rather than waiting for a developer to notice it manually. This shifts the burden from discovery to decision-making, allowing teams to focus on validating updates rather than tracking them. Even with automation, dependency updates should not go directly into production. Staging and canary releases offer a safer way to validate changes. A staging environment replicates production as closely as possible, giving teams a controlled space to test for regressions. Canary releases take it a step further by rolling out updates to a small portion of users or systems before full deployment. If something breaks, the blast radius is limited and rollback is easier. For instance, a new database driver could first be deployed to a single node serving a fraction of users. If the node behaves as expected, the update can gradually expand. These release patterns ensure that dependency updates are tested under real-world conditions without risking a system-wide outage. Sometimes updating to the latest version immediately is not feasible, particularly when a major release introduces breaking changes. In those cases, backporting becomes an important strategy. Backporting involves applying a security fix from a newer release to an older, pinned version. This allows organizations to remain secure while maintaining stability. Consider a legacy application locked to version 2.x of a library that is now at version 4.x. Instead of forcing an upgrade that might break compatibility, developers can integrate the security patch into the older version until they are ready for a full migration. This compromise acknowledges the tension between security and functionality, giving teams breathing room without leaving systems exposed. When updates cannot be applied immediately, runtime mitigations help reduce risk. Feature flags can disable vulnerable functionality until a safe update is ready. Virtual patching, often implemented through firewalls or intrusion prevention systems, can block known exploit patterns without modifying the application code itself. These temporary controls buy time for teams to implement permanent fixes. For example, if a vulnerability is discovered in a web framework's file upload function, a feature flag might disable uploads for certain workflows while a patch is developed. Runtime mitigations are not a substitute for updates, but they are valuable tools for bridging gaps in high-pressure situations. Secure builds are another cornerstone of dependency management. Hermetic, isolated builds restrict network access and external influences during compilation. This means the build process relies only on known, vetted inputs, not live fetches from the internet. By removing outside variability, hermetic builds reduce exposure to supply chain attacks and guarantee repeatability. Imagine cooking a recipe where all the ingredients are pre-measured and sealed in advance. You are far less likely to end up with contamination compared to pulling items off a crowded supermarket shelf in real time. This isolation adds predictability and trust to the software supply chain. Reproducibility extends this concept further. A reproducible build guarantees that given the same source and inputs, the build process will always yield identical artifacts. This consistency allows teams to verify authenticity by comparing outputs. If two independent parties build the same source and their results differ, it signals potential tampering. Reproducible builds act as an integrity check on the software supply chain. They are particularly valuable for security-sensitive projects where trust in the final artifact is paramount. The principle is much like financial auditing. Consistent numbers across independent records validate accuracy, while discrepancies raise red flags. Not every risk can be addressed immediately, which is why organizations adopt risk acceptance workflows. These workflows document decisions to defer certain updates, explain the reasoning, and outline compensating controls. For example, a team might justify deferring a minor update due to lack of test coverage, while noting that firewall rules are in place to mitigate the associated risk. Importantly, deferrals should include expiry dates, ensuring that risks are revisited rather than forgotten. Risk acceptance acknowledges that resources are finite and perfect compliance is unrealistic, but it frames those choices within a structured, accountable process rather than informal neglect. Code review plays a vital role when updating dependencies, not just for checking syntax, but for understanding the wider impact. Reviewers must examine transitive dependencies, configuration changes, and deprecation notices in release notes. A simple version bump may introduce new defaults or remove previously available functions. By scrutinizing these details, reviewers catch issues that automated tests might miss. For instance, a library update could silently change how encryption keys are handled, with profound implications for compliance. Treating dependency updates with the same rigor as feature code ensures they integrate smoothly into the broader system. Production monitoring is critical even after updates are deployed. Systems must track new vulnerability disclosures against shipped SBOMs and generate alerts when affected versions are in use. This continuous monitoring closes the loop between dependency management and operational security. Without it, teams risk shipping vulnerable software and remaining blind to emerging threats. For example, if a zero-day vulnerability is disclosed in a widely used library, monitoring tools can immediately flag which applications include it and trigger a response. Monitoring makes the difference between learning of an exposure from internal alerts versus reading about it in the headlines after an incident. When malicious packages are discovered, organizations must respond decisively. Incident response procedures for this scenario include recalling affected artifacts, rolling back deployments, and conducting indicator of compromise hunting to detect signs of misuse. This might involve scanning logs, searching for unexpected network connections, or auditing file changes. The goal is to contain damage quickly while restoring trustworthy versions. Just as with other forms of incident response, preparation is key. Having predefined steps allows teams to act swiftly under pressure, minimizing both downtime and risk of data loss. A fork strategy provides a long-term solution when upstream projects become unresponsive or abandoned. By forking the code, an organization assumes responsibility for maintaining the library, applying patches, and ensuring compatibility. While this adds overhead, it also secures the future of critical components. For instance, a company might fork a widely used library that has gone dormant, then allocate internal resources to maintain it. This approach guarantees continuity but requires a clear governance model to prevent fragmentation. Forking should be seen as a last resort, but when executed responsibly, it ensures stability in the face of upstream uncertainty. Supply chain levels for software artifacts, or SLSA, is a framework that defines maturity levels for provenance and build integrity. It provides a roadmap for organizations to improve the trustworthiness of their software supply chains. At the lowest levels, SLSA focuses on basic integrity, while higher levels require robust, tamper-resistant processes with detailed provenance. By aligning to SLSA, organizations can benchmark their practices and demonstrate assurance to customers and regulators. It is analogous to food safety certifications. Each level reflects a higher degree of control and reliability in the production process. Evidence artifacts are the records that prove an organization is following its policies for dependency management. These include SBOMs, signature verification logs, approval records for updates, and test results. Collecting and retaining these artifacts enables both internal audits and external compliance reviews. They provide the paper trail that demonstrates due diligence in managing open-source risk. Without such evidence, even well-executed processes can appear ad hoc. Evidence artifacts transform security practices from implicit trust to demonstrable accountability, which is increasingly demanded by regulators and customers alike. It is also important to avoid anti-patterns that undermine dependency management. Relying on unpinned latest tags leaves builds unpredictable and vulnerable to upstream changes. Using unaudited mirrors bypasses the safeguards of trusted registries and risks introducing malicious code. Rolling out updates without rollback plans courts disaster, since a single failure could cause widespread outages. These anti-patterns reflect a lack of discipline and preparation, turning manageable risks into systemic weaknesses. Recognizing and eliminating them is just as crucial as implementing best practices. For learners preparing for exams, it is worth noting how these concepts map directly to secure and dependable software delivery. Tools like SCA and SBOMs provide the visibility needed to manage vulnerabilities and licenses. Controlled update strategies ensure that fixes are applied without destabilizing applications. Compliance frameworks like SLSA offer a way to benchmark maturity and demonstrate trust. Together, these practices embody the principles of modern cybersecurity, where open-source use is not avoided but embraced responsibly. Understanding them is not only practical for day-to-day work but also directly relevant to exam scenarios. In summary, controlled sourcing, verified integrity, disciplined testing, and careful attention to licensing form the foundation of trustworthy open-source dependency management. By approaching dependencies as part of the supply chain, organizations reduce risk while maintaining the agility that open source makes possible. Transparency through SBOMs, discipline through update policies, and resilience through incident response ensure that applications remain secure and reliable over time. The path forward is not about eliminating open source, but about mastering its use so that every component contributes to security rather than undermines it. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.